Everyone, my name's Ben Sachs. For those of you who don't know me, my company, Sachs & Associates, offers training in C and C++ for companies all over the world. And I'm here to talk a little bit about value categories in C and C++. And the first thing I want to mention is that value categories aren't language features, not in the sense that the ability to do things like overload operators is a language feature. The value categories are part of how the compiler understands and interprets expressions in the language. So understanding what these value categories are and what they mean will help you understand how the compiler thinks, which is helpful both because it helps you decipher some error messages that might otherwise be confusing, and it also provides some insight into why certain features of the language, like operators and references, work the way that they do. Now, originally there were only two value categories, lvalues and rvalues. Back when they were first introduced in C, they were relatively straightforward and simple concepts. Then C++ came along. It added classes, const, references, and those concepts needed to evolve to handle the new possibilities that these new language features offered. And then we got along to modern C++, and rvalue references were introduced. And this further complicated the situation. The concepts had to evolve yet again, and they also had to introduce new types of value categories to describe exactly what the language was doing in various places. So in this talk, I'm going to kind of walk you through this evolutionary process. We'll start from the early view of where these terms came from, and then I'll gradually refine the picture as we go. So there's a lot of material to cover. I'm going to try and speak relatively quickly. Feel free to ask questions as I go so. You may want to come up to the mic here if you decide to do that. But you should be prepared for the possibility that I'll say, that's coming up in a future slide. Okay, so the terms lvalue and rvalue come from assignment expressions. The idea is the L means left. The thing on the left-hand side of an assignment statement, the thing being assigned to, has to be an lvalue. So what's an lvalue? It's any expression that refers to an object. Okay, that begs the question, what's an object? An object is a region of storage. It's something that has a defined location in memory where it lives. So let's take a look at a simple assignment statement here. We have an integer n. We're assigning 1 to that n. So here, there are several expressions in that assignment statement. N is an expression, 1 is an expression, and the whole thing, n equals 1, is also an expression. So in here, n is the sub-expression that refers to an integer object. It's an lvalue, and that makes it the sort of thing that can be assigned to. 1 is also a sub-expression, but it is not an object. It's just an rvalue. An rvalue is something that isn't an lvalue. So anything that isn't an lvalue is an rvalue. Now, I showed you, the example I just showed you used relatively simple expressions, but those expressions can also be more complicated, as in this example. So here the left-hand side is made up of several tokens. It's x sub I plus 1. The right-hand side is the absolute value of p arrow value. Both of those are sub-expressions. And the same rules apply. The thing on the left-hand side has to be an object that can be assigned to. In this case, it is. It's the I plus 1 member of the array x. So it has to refer to an object. The right-hand side can be either an lvalue or an rvalue. We can assign from either lvalues or rvalues. So any expression will work on the right-hand side. So why does this distinction exist? Why did the language designers introduce these two categories in the first place? It lets the compiler generate code more efficiently than it would be forced to do if Rvalues were required to occupy storage in memory. So let me give you an example. Going back to the n=1 assignment statement here. So it's possible that the compiler will choose to place that value 1 in data storage. Even though it doesn't have to put it there, it may choose to put it there as if it were an lvalue. So in this case, in the assembly language, we would have a portion of the executable that is reserved for that value 1 in data space. And then the assignment statement might look something like this, where we move the value from 1 into the location designated by n. On the other hand, the compiler might choose to do things like this. There are many architectures that offer what are called immediate operands, where the value to be operated on doesn't have to be a separate data value. It can actually be built into the instruction like this. So in this case, the value 1 appears directly in the move expression. So there's no data storage associated with that 1. It doesn't appear anywhere in data space. It's part of the code space built into one of the instructions. If Rvalues had to occupy memory, the compiler wouldn't be able to do this sort of thing. So suppose that I wrote the assignment statement the other way around. I said 1=n. Now, we know we can't do this, but why can't we do this? It's not because of types. N is an object of type int. 1 is a literal, which also has type int. They are the same type, but it's not valid because the thing on the left-hand side has to be an lvalue, and 1 isn't an lvalue. It doesn't necessarily live at any defined place in memory. So every expression is either an lvalue or an rvalue. Lvalues refer to objects that live in memory, Rvalues don't. Kind of. This is true for built-in objects of built-in types. The picture is a little more complicated when we're talking about class types. I'll explain that a little bit later on. So what sorts of things are Rvalues? Well, literals, as I've shown you, so values like 3, 3.14159, character literals like a, these things don't have to occupy data storage. It turns out that string literals like x, y, z, z, y here do have to occupy storage because these things have to behave like arrays. You need to be able to step through them with a pointer. And in order to do that, the thing has to live at a well-defined location in memory. So lvalues can appear on either side of an assignment statement. As we know, the thing on the right doesn't have to be a literal value or something like that. It can also be an object that we're assigning from. And in this case, we're using the value n as an rvalue. We're assigning from it. And the language refers to this under a special term, lvalue to rvalue conversion, which is sort of the standards way of saying that we're reading the value from n. When we care about something being an lvalue, we care about where that value lives. When we care about something being an rvalue, we care about what value it holds. So the concepts lvalue and rvalue come from assignment expressions, but they apply in lots of other expressions as well. So for example, let's look at the plus operator. By the way, lvalues and rvalues are one sort of restriction that can be applied to operators like this, but there are others. The things being added have to have types that are compatible, for example. So the operands of the plus operator can be either lvalues or rvalues in either order. Whether I add x plus 2 or 2 plus x doesn't matter. On the other hand, what about the return value? Where does the result m plus n go? It doesn't go in m, it doesn't go in n. It goes into a temporary location, maybe a CPU register. And that sort of temporary object is an Rvalue. It's not guaranteed to have memory storage associated with it. And so as such, just like you can't assign to the literal 1, you also can't assign to the result of m plus 1, because that's an Rvalue. There's nowhere for the assignment to assign to. So another operator that we'll look at is the unary star operator. So unary star yields an Lvalue. When we dereference a pointer, star p is an Lvalue. It's something that can be assigned to. So here we have an example. We have an array of integers. We have a pointer pointing to one of the elements in that array. We also have a character pointer that's initialized to null. So that assignment there, star p equals 3, is valid because star p is an Lvalue. It lives at a particular location in memory. Star s is actually also an Lvalue. Now, I shouldn't do something like this where I assign a value to it because it's pointing to null, and that would give me undefined behavior. But from the compiler's perspective, Lvalueness is totally evaluated at compile time. The assignment is problematic for other reasons, but in terms of Lvalueness and Rvalueness, it's perfectly valid. So here's how you think about data storage, because when the optimizer gets involved, things change a little bit. When we think about Rvalues, we don't think about them as occupying data storage. As it turns out, some of them might. I showed you that example of the immediate operands that are built into instructions earlier. That worked well because I was using a small operand, 1. But there's only a limited amount of space in the instructions that can be given over to these immediate operands. So if I had a very large value, like 1 billion that I was trying to assign, that might not fit in that space. And in that situation, the compiler might fall back on giving that Rvalue storage in memory. So it turns out some Rvalues might be in memory, but you're required to program as if they don't. The compiler has to have the freedom to not put an Rvalue in memory. We think of Lvalues as occupying data storage. Now, once the optimizer gets involved, it might optimize away some of that storage. But it will only do that when you won't notice. So you, as the programmer, are always allowed to program as if an Lvalue has a location in memory. And then the optimizer might just come along and make things a little bit faster or more space efficient. Now, on the other hand, Rvalues of class types, we do think of those as occupying data storage. So why do those have to be different? Well, let's take a look at this example where we have a struct that's made up of 2 integers, x and y. By the way, when we talk about the standard refers to objects of class types. And when it talks about a class type, it means anything that's a class, a struct, or a union. So here we have an object of type S, S1, initialized with the values 1 and 4. So what would it look like when the compiler generates code to read from the Y data member of that object? When, in this case, S1 is an Lvalue of type S. It depends on how it's being used in the expression. We don't say that S1 is an Lvalue. We say that when it's used in this expression, it's being used as it is an Lvalue. So this assembly code is a little bit more complicated, but what I want you to notice here is that the process of reading the Y data member, it happens in 2 steps. The first one is that it takes the address of the S1 object here and places that into a register. And then it uses that register as the base address of the S1 object and performs a calculation using that base address to find the Y data member. And then it reads from that location into another register, R2. And then once it has that value, then it can go ahead and store that value into the location designated by I. So there's this calculation going on that involves a base address. So what would it look like if we were dealing with an R value of type S, like the return value of this function foo here? So in this case, the compiler still needs to go through a similar process to access the data member Y of that return value, which means that if it's going to perform that base plus offset calculation to get at Y, the return value of foo has to have a base address. When something has a base address, it occupies a location in memory. We think of it as occupying storage. This is why R values of class types need to be treated a little bit differently. We'll refine this picture a little bit as we go on, but this is just the first approximation. So it turns out there are lvalues that actually can't appear on the left-hand side of an assignment statement. This is one of the cases where once C++ got involved, those concepts became more complicated. Because in C++ we can have const objects, like this array name here. So if I try and assign to one of the elements of name, the elements of a const array are themselves const, I can't do that because it's a const object. It can't be modified. It still has a location in memory. It's an lvalue, but it's a non-modifiable lvalue. And this term is actually used in the standard. I didn't just make that up. So this distinction between lvalues, non-modifiable lvalues, and rvalues gives us a vocabulary for explaining certain differences in the language. So for example, here, I have an enumeration constant called max. I have a single enumeration, unnamed, that contains a single value called max that I expect to use in expressions as a constant integer. This value max, when it's used in an expression, it behaves like an R value. So I can't assign to it like this. I can't change the value of max because max is an R value. I also can't take its address. I can't set up a pointer to point to the location where that value max lives because there isn't necessarily a location that does that. It's an R value. But if I make max a constant integer object like this, then it becomes a non-modifiable lvalue. I still can't assign to it because it's not the kind of thing that can have its value changed, but I am allowed to take its address. I can set up a pointer that points to the location at which max lives in order to pass that pointer around. Max is an lvalue here. So here's this table gives you the summary. Lvalues are both addressable and assignable. Non-modifiable lvalues are addressable but not assignable. Non-class R values are not addressable and not assignable. Again, it's a little bit more complicated for class R values, as I explained. So, when we think about this distinction helps us explain the behaviors of references. So, for anyone not aware, references behave very much like pointers in C++. When I create a reference to an int, ri here, and I bind it to an int I, that essentially sets up ri as an alias for I at that point. Anytime I go on to use ri in an expression after that, the code behaves as if I had written I instead. So references, the standard takes great pains to say that references and pointers are different things. They're not necessarily implemented the same way. But in practice, you can almost always think of them as being the same. And a lot of code that uses references could also be rewritten to use a constant pointer instead. Not a pointer to const, not something that points to something that can't be modified, but a pointer that itself can't change to point to anything else. Because a reference, once it's bound to a value like I, it is always bound to I. There's no way to rebind it to something else. So the closest analogy with pointers is a constant pointer that always points to the same thing. And then anywhere that we would have used Ri with a reference, we can use star CPI as a pointer. And so just like star CPI yielded an lvalue, references are also lvalues. So why did the language choose to introduce references if they complicated things like this? The real reason that references are in C++ is to make overloaded operators work the way that you would like. One of the design philosophies in C and C++ is that built-in types and class types should behave very much the same. You should be able to write a class type that looks like a built-in type. And if we don't have references, it's really hard to write overloaded operators that give us that behavior. So here is an example. We have an enumeration type month that represents the different months in the year. In the original C, enumerations were basically just integers. It was a paper-thin disguise over an int. So I would have been allowed to write code like this, where I loop through all of the months, and using a variable of type m, and I do ++m. That compiles and runs in C. It doesn't work in C++ because enumerations are treated more like distinct types in C++. So if I want to make this work, I would need to overload the ++ operator for month. So let's try and do that without references, and I hope you'll see why references are so important. So here, we're writing the ++ operator as pass by value. We just pass in the value of a month. We go ahead and add 1 to that month value. We have to use a static cast to turn it into an integer. It will convert to an integer automatically, but then we need to convert it back into month to update the value of x. Except that updating the value of x doesn't really do what we wanted, because I can write ++m, but it doesn't actually change the value in m. M was passed to x by value, so x gets incremented, but m doesn't. So this doesn't give us the behavior that we want. Even worse, because in this situation, I'd be allowed to apply the ++ operator to an Rvalue, like the April value here. That's not something you can do with the built-in operators. If you have an Rvalue of type int, like 42, you're not allowed to apply the ++ to it. So, okay, pass by value didn't work. Let's try pass by pointer instead. So here, we would be taking the value, the month that we want to point to by pointer. Turns out you can't even write this. It just doesn't compile. Overloaded operators in C++ can't have parameters of pointer types. But let's suppose it did compile for a moment. It still wouldn't look the way that we want it to look. It doesn't behave like the built-in types, because ++m isn't what you would write. The thing that you would have to pass off as the argument to this function would be the address of m. So whereas you would write ++i to increment an int, you'd have to write ++m to increment a month. And that just ruins the whole thing. It destroys the illusion that we're trying to create, that built-in types and user-defined types like month behave the same way. So we really need references in this case. We need something that behaves like a pointer but doesn't force us to take the address of the thing when we're passing it in. So here, we pass in the value of the month by reference. We can update the value inside there, and now as a result, ++m actually changes the value that it's applied, the value of the argument that it's applied to. It works the way that we want, and as a bonus, in this case will only work on lvalues. References won't bind to rvalues because rvalues don't have a well-defined location in memory. There's not necessarily a place where April lives that we can update its value this way. Now, by the way, if I were really writing a plus plus operator, it doesn't return void. It returns a reference to the thing that's incremented. I didn't want to distract the discussion before this point with that, but this is what it really looked like. Okay, so we can also have parameters that are referenced to const. And references to const will bind to objects that are either const or non-const. References to non-const objects will only bind to modifiable objects, non-const objects. So in this case, this function would accept any t object, whether it was constant or non-constant. Inside the function f, it would be a reference to const, and it would behave like a non-modifiable lvalue. Something that has an address, but I can't change the value there. So this function winds up behaving very much as if I had written the same function using pass by value instead, in the sense that if I write f, and whether I'm passing by value or by reference to const, I know that the call to f isn't going to change the value of x, because if I pass by value, the function only sees a copy of x. It doesn't see the value of x itself. It can't change x. If I pass by reference to const, the function sees a non-modifiable lvalue of type reference that is bound to x. It can't change x because x is treated as const in that situation. So why would I want to make a why would I want to do these things, pass by reference to const instead of pass by value? Passing by reference to const might be more efficient. Making a copy of a value is required when you pass by value. If you're talking about a class type that's very large, that copy could be a very expensive thing to do, whereas binding a reference to something is very cheap. The cost doesn't go up as the object gets bigger. So, as I mentioned before, a pointer to a t object can only point to an lvalue of type t, and in the same way, a reference to non-const t will only bind to an lvalue of type t. So, I can't take the address of 3 and assign it to a pointer to an integer. And in the same way, I can't bind a reference to an integer to the literal 3. Neither of those works because 3 is an R value. For the same reason, I can't set up a pointer to an object that isn't of the right type for the pointer to point to. So I can't make a pointer to a double that actually points to an integer. Even though I is an L value here, it's an L value of the wrong type. So I can't take the address of I and put it in a pointer. I also can't bind a reference to a double to I, because I is an int. Well, sort of. There's an exception to that rule when we get into references to constant objects. It turns out that a reference to a const t can bind to an expression x that's not an L value of type t, as long as there's a conversion from whatever type x has into the type t that the reference wants to bind to. The way that this works is that the compiler creates a temporary object that holds the value of x converted into a t object. And that temporary object that was created, that's what the reference winds up being bound to. That temporary object has some sort of location in memory that the reference can refer to. So here's an example. I'm allowed to write a reference to a constant double, rd, and bind that to a 3. And the way that it would work is 3 is of type int, So the compiler would first convert that 3 into a double with the same value. It would put that converted value into a temporary object of type double that holds the result of that conversion, and then it would bind RD to that temporary object. That temporary object would last as long as the reference RD lasts. When RD is destroyed, the temporary is also destroyed. So why is this so special? Why do things in this special way? Why does reference to const have to behave this way? And it's done so that pass by reference to const is a viable replacement for pass by value. We want to be able to pass by reference to const instead of passing by value because it might be cheaper than passing by value. But think about what happens if I pass by value. So here I have a function f that takes a long double by value. I can pass it a long double value, like x there, in which case we just generate a copy of x, pass that off as the argument to the function. On the other hand, I can also pass in values that aren't long doubles, like this integer 1 here. The literal 1 is of type int. When the compiler generates the code for that, it will convert the 1 into a long double and pass that as the argument to the function. Pass that converted value as the argument to the function. So in order to make reference to const work the same way, it's important that I be able to pass not just a long double to a function that expects to take a reference to a constant long double, but also something like an integer. In this case, an integer that is an Rvalue, in which case we create this temporary object and bind the reference to that. And it's perfectly safe to do that, to bind the reference to that temporary, because it's non-modifiable. There's no danger that someone will call this function expecting to get back a modified version of 1, because the thing has to be treated as const inside f. So either way, the function calls essentially have equivalent behavior from the caller's perspective. So I talked before about how normally we think of Rvalues of built-in types as not occupying storage. Rvalues of class types do occupy storage. This temporary object that we've just created as part of doing this reference binding, that also occupies storage. It has to, because the reference has to have a place in memory to refer to. And this works even for built-in types like long double. It's not true just for class types. So this is another way that you can have Rvalues that have locations in memory, that occupy data storage the way that Rvalues of class types do. It turns out in modern C++ there are 2 kinds of Rvalues, and they have special names. There are pure Rvalues, or PR values, which don't occupy data storage conceptually. And then there are what are called expiring values, or Xvalues, which do occupy data storage. Both of these are considered to be types of Rvalues. So when I refer to Rvalues going forward, I could be talking about either a PR value or an Xvalue. It turns out, as the programmer, you don't need to worry that much about the distinction of what an Xvalue is. It's mostly in the standard to describe the behavior of the language so that compiler authors know what needs to be done. You as the programmer don't usually think in terms of Xvalues, but I wanted to make sure that you were aware, that you had some understanding of the term, because I know that a lot of people are familiar with it, but don't necessarily know what it means. So, when the temporary is created as part of binding this reference to a constant object to an Rvalue, it's created through what's called a temporary materialization conversion. It's a conversion that turns a PR value that doesn't have a location into an X value that does have a location. So that's what's going on there. So suppose that let's revisit the idea of overloading operators, and let's look at how would we create an overloaded plus operator for a string type that concatenates two strings together, that behaves in a way that looks very much like the way that the built-in plus operator behaves for objects like integers. So here's just a rudimentary version of the string class. It has a copy constructor. It has a converting constructor that allows us to treat string literals as string objects. And it also has an assignment operator, a copy assignment operator, to be specific. And then we have our plus operator that will concatenate two strings together. So the plus operator takes its arguments by reference to const, which means that they will bind to either lvalues or rvalues of the appropriate type, which means that I can write something like this, where I have two strings, s and t, and then I can add those together so that I say s plus the string literal containing the comma plus t. And the compiler will interpret it like this. It will see that that string literal can be treated as a pointer to constant character. We have a converting constructor from pointer to constant character into a string. So it will first apply the converting constructor there so that we have all operands of type string in that case. And the result of doing that conversion is that the string that's created is an Rvalue. It's a temporary object. And whereas s and t in this expression behave like lvalues. On the other hand, the function returns the result by value. So the result of calling that function is an Rvalue. You can't take its address and set up a pointer that will point to it the way that you could for s or t individually. So up until now, I've been referring to just references. That's the way that these things work, that references referred to in C++03. All there were references. In C++11 and beyond, we now have two different kinds of references. We have lvalue references, which are the references that existed before in C++03. And we also now have Rvalue references, which are a new feature introduced in modern C++. So lvalue references behave the same way that references did before Rvalue references were introduced. So lvalue references are declared with a single ampersand operator. Rvalue references are declared with a double ampersand operator. So here, Ri is an Rvalue reference to an int. Unsurprisingly, an Rvalue reference can bind to an Rvalue, like 10 there. So Rvalue references can appear in lots of different places, but they're typically used as function parameters and function return types, just like lvalue references are traditionally. We usually don't create reference objects on the stack and pass them around. They're usually used as function parameters and return types. And you can have Rvalue references to const, like this. It's usually not a particularly useful thing to do, because as you'll see, Rvalue references are in the language to implement something called move semantics, which usually expects the thing to be treated as, the thing being referred to be treated as modifiable. And an Rvalue reference to const refers to a non-modifiable object. So Rvalue references will only bind to Rvalues. Even an Rvalue reference to const will not bind to an lvalue. It will only bind to an R value. So here, if I have an integer n initialized with the value 10, I can't bind an R value reference to n, because n is an L value. It's not an R value. Even if I'm trying to bind a reference to an R value reference to const to it, it doesn't work. When I bind the R value reference to an R value, that triggers a temporary materialization conversion, that thing that turns a PR value into an X value. The same way that binding an L value reference to const to an R value triggered a temporary materialization conversion. Similar behavior in both cases. So as I mentioned, R value references are in the language to mainly to implement move semantics. They provide a mechanism by which, in some situations, we don't want to copy an object. It's cheaper if we can, instead of if we want to take the value from one object and put it into another object. If we need to preserve the value in the original object, then we need to make a complete copy of that object into the new object. But if we don't care about preserving the value of the original object, for example, if it's only a temporary object like an R value, then we might be able to implement the transfer of value more efficiently by moving that value, just stealing the contents of the thing that we're assigning from and placing them in the thing that we're assigning to. That's a move operation. So in this case, the class string has both copy operations that take their parameters by reference to const, and move operations that take their parameters by R value reference to non-const. If they took the parameters by R value reference to const, they would still be binding to R values, but those R values would be treated as non-modifiable. And the purpose of being able to do a move operation is that we want to be able to destroy the thing that we're moving from, because that might provide us with a more efficient way of getting the value that we want into the object that we want. So here are some objects, 3 objects of type string, S1, S2, and S3. If I assign from S2 to S1, that performs copy assignment. S2 in this expression designates an L value. It's not expiring, so the value has to be preserved, which means it has to be copied. It can't be moved from. On the other hand, if I assign from an R value, like S2 plus S3, the result of that plus operator that I showed you a moment ago, that will perform move assignment. It's safe to move from the result of S2 plus S3 because that's a temporary object. It's going to die as soon as we reach the end of that statement. So it's perfectly safe to move the value out of S2 plus S3 into S1 because S2 plus S3 is going away. It's sort of, I like to think of this as C++ providing a way for S1 to say, hey, are you going to eat that? Because if you're not, I'll take it. So when you bind an R value reference to an R value, it performs one of those temporary materialization conversions. It creates an X value, an expiring value. But let's look at the code inside the move assignment operator here. That R value reference is a parameter to the function called other there. Now let's suppose somewhere inside this operator, I wanted to create a string temp using the value of other. Would this perform copy construction or move construction? It turns out it performs copy construction. It's not treated like an R value that I could move from. It's treated like an L value because from the perspective of the caller, the thing behaved as an R value. It was about to die at the end of the statement. It was safe to move from. But inside the function, this function could be hundreds of lines long. I hope it isn't, but it could be as long as I want. So from the perspective of people inside this function, the object other looks like it has a fairly long life. It lives as long as the function does. So it needs to be treated as something that doesn't expire, like an lvalue. And the general rule here is pretty simple. If it has a name, it's an lvalue. If it doesn't have a name, it's an rvalue. It might be an rvalue, I should say. Not necessarily. Unnamed things aren't necessarily rvalues. Named things are almost always lvalues. So there are some situations, though, where it does make sense to move from an lvalue. So here, the most common example is swap here. If I were to, before the advent of rvalue references, a swap function would typically be written something like this. So I take in two values, a and b. I copy the value from a into a temporary location. I overwrite a with b, and then I copy the value that was in a, it's now in the temporary location, into b. Even if T has a move constructor and a move assignment operator in this case, if it's written like this, the compiler will generate code that performs copy construction and copy assignment in this case. Because the compiler doesn't see A, just focus on the first case here where we're creating the object temp from A. A doesn't look like it's expiring to the compiler. It lasts as long as the function does. But as the programmer, we can tell the very next line overwrites the value of A. There's no need to preserve it. It would be safe to perform a destructive copy, aka a move, when we're from A to create temp. So it's safe to move from an lvalue if it's expiring, but the compiler can't always tell when an lvalue is about to expire. In some cases, the programmer has knowledge, but the compiler can't easily discern. So how can we tell the compiler that an lvalue is about to expire? We need to convert it into an xvalue, an expiring value. Specifically, we need to convert it into an unnamed rvalue reference, something that designates an object, but it designates a temporary object that's about to expire and can be safely moved from. And that's what the standard move function does here. When I call move on an object, that effectively performs a conversion from that object from lvalue into xvalue. Now, what I'm showing you here is a somewhat simplified version of the function move. If you go look at the way that it's defined in the standard, it actually looks more complicated than this. But I want you to focus on the fact that it returns an rvalue reference to a t. Return values don't have names, so the result of a move is an unnamed rvalue reference, an xvalue. Again, as a programmer, we don't often think about xvalues because we're usually thinking about something as either a long-lived value like an lvalue or a short-lived value like an rvalue. But this term xvalue is mainly there for compiler writers to describe this slightly in-between state that objects can be in. So the actual way that it's described in the standard looks like this, is that there are expressions, and expressions break down into two categories. There are values and generalized lvalues, GL values. And then what I've usually been calling an lvalue up to this point is one kind of GL value. An lvalue only behaves like an L value. It has a location in memory. A PR value, a pure R value, always behaves like an R value. We have to treat it as if it doesn't have a location in memory. An X value behaves like both. It behaves both like an L value and an R value. And so that's what's going on in this picture. That's the final truth that the standard has at the moment. That brings me to the end of the talk. So I'm happy to take questions at this point, but otherwise, I hope you find it useful. Good luck in your programming.
When do lvalues implicitly become xvalues?
I'm sorry, when did lvalues what?
Implicitly become xvalues.
Implicitly become xvalues?
Yes.
Was that the question? Okay. When do lvalues implicitly become xvalues? Essentially in return statements. It's a little, the standard uses more complicated terminology than that, but almost always when you think of an L value that is being converted into an X value, and you don't need to explicitly move from it, it's usually in a return statement.
Thank you.
Yeah. Do you want to use the microphone? Okay. The question is did I say that a string literal is an L value, and did I really mean to say that? Yes, I did. The string literals have to have some location in memory because, so a string literal is really an array underneath. An array has to have elements laid out in memory in some kind of sequential order so that you can do things like step through it with a pointer, like we often do with string literals, say, if you wanted to take the length of it with strlen. What says that you can't assign to a string literal? You can't really, it's because we often think about string literals as being pointers to constant characters, but that's not actually their real type. Their real type is array of constant characters. And you can't assign to an array in a blanket form. So if you tried to put a string literal on the left-hand side of an assignment statement, you'd be assigning to a complete array, and the language just doesn't let you do that. I'm happy to, if you don't want to use the microphone, I'm happy to have you come up and ask me questions more individually. As I said, otherwise though, as I said, good luck in your coding endeavors, and I hope you find this stuff useful.